Today, Terrence's talk is on debug and fault isolation strategies as the industry moves towards 3D IC. Terrence has been with Intel Malaysia for 16 years. He has been a test technologist for his entire career. Terrence is currently a senior principal engineer in manufacturing and product engineering organization. Thank you, Terrence. And Terrence will take questions at the end of his presentation. If you have any, please post them in the Q&A.
Thank you, Zoe. All right. First of all, I'm Terrence. Good morning, good afternoon, good evening, wherever you are. So I'm going to kick off this today's chiplet sessions, where I'm going to talk about debug and fault isolation strategy as the industry moves towards a 3D IC. So there was a chiplet road to integrations architecture earlier this month, where there's a talk about the architecture and something about tests. So today I'm going to talk a little bit about when you test, there are some challenges around how do you debug and isolate the faults, all right, in this complicated 3D IC world. So my outline is going to be test and debug challenges, and how do we achieve 100% package test equivalence at bare die. This is one of the important concepts when you go to 3D IC. And what are the package tests, with inline debug fault isolation capabilities? What are the important considerations, DFT, that one need to implement when you go to 3D IC? And what are the call for actions and a summary? All right, if you attend the chiplets architecture sessions back in July, Phil Knight from Broadcom actually talked about some of the test challenges. And I just want to quote some of his statement about, when you do assembles 30 bare die with 99% quality, you're going to have a final package yield loss of 26%. Yes, this is a true fact, right? When you have multiple chiplets, multiple dies assembled, and the question is that how do you debug and isolate the failure at final package test? You're going to see yield loss, right? Even though your quality is 99%. And what is needed in each chiplet, and the bare die supplies, because your chiplets may come from different suppliers, to provide effective debug and fault isolation at the final test. And how do we make use of the debug capability for each die at the package level, right? So that is in response to the final package loss that one will experience. Now, the second statement is about known good die. When you talk about 3D IC, 2.5 the people talk about known good die. Known good die, does not mean all chip die will pass package system and fail, right? This becomes a defect per million, quality, right? How do you deal with fail return, right? And how do you debug system failure, which is a measure of a DPM? Because in some of the tests, we may insert a system level test in-house as a last measure of DPM before we ship out to the field test. So my presentation will answer some of these questions in terms of debug and fault isolations. All right, now, the first thing, I would like to call out, in reference to last year's ITC paper that we published. When you go take, for example, an Intel 4 rows, right, where you have a top die and a bottom die over here, you're going to have a challenge in the physical FA and probing, right? Unlike monolithic, you can directly do a physical debug on the silicon substrates. But when you have like a embedded, like an active interposer, you're going to have a challenge in terms of FA and probing. So it is important that, successful defect finding and time to root cause is key. And we'll achieve that to three things, which we're going to talk about. How do you achieve 100% package equivalence at bare die? What you need to do at final package to inline during the production test to enable you to get the isolation information quick, and what are the debug hooks that support the above. All right, now the first thing is about this is a chiplet, right? In a chiplet, I'm going to show what are the DFT needed in order for us to achieve 100% package equivalence. To me, this is a foundation of every chiplet that we need to do for debug and also test, right? The first thing is about direct IO control. If you look at, we need to have direct control on clock and reset. Test port, you need to have a monitoring I/O for debug, power rail, and of course, how you deal with your high-speed I/O transmit and receive. That's number. You need a direct control so that you can apply it onto during the wafer test. The second thing is about, it is very important that, for an IP with a logic and memory block, as part of the debug mechanism, we need to, even though we do a structural test or functional test, there will be a need to dump out the state of the registers, be it a logic states or a memory states. In order to do so, we need to deterministically halt the chiplets when it's running and dump it out. Deterministically is the keyword, so that you're able to capture the right failure moment of interest. The third thing is about analog monitoring, right, and digital monitoring. You need to, or have a way to monitor it, through the monitor hub in the analog block, like a voltage monitoring or some kind of clocks, PLL signal, something like that. And number 4 is very important, right? You're going to notice that these are the micro bumps, and you don't probe all the micro bumps because of the known challenges in probing the micro bumps. So there are cases where all the clocks, some of the test ports, they could be, when you integrate in the full package, they are like interoperations to other chiplets. That's why you need to have a JTAG overrides to take control at the chiplet levels. So having these 1, 2, 3, 4 things will enable us to achieve 100% package equivalence for test and debug at the bare die. All right, next, I'm going to show about what you need to do at the package test. Just like I mentioned, what you needed at the chiplet, right? So that you can produce the 99% quality, right? Or reproduce a failure later on. I'm going to talk about at the die level. Then after that, the die will come package. You come to final package test. In the past, when you do the monolithic fashion, you're just going to do open shots and start doing your scan tests, memory tests, I/O test. Now, if you take, for example, of this complicated 3D structure with an active interposer, you need to break down your, I call it your test modules into a few blocks of, I call it debug modules, where I call it inline in the way that this thing need to be part of the production test program, where it tells you what is failing, which I'm going to walk through. There are, 1, 2, 3, 4. There are 5 things that you see on the box. The first thing is what I call assembly screen. Now, you know that there will be unique failures introduced when you integrate the chips into a package, right? I call it assembly screen. They are like package for open shots, which is similar to conventional monolithic. There could be C4 bumps, open shots, and unique to 3D IC is going to be TSV. All right? You need to be able to have a way to check for open shots. The second thing is about test access mechanism, because the way you access the chiplets, the test access will be different between wafer and package. And you need to be able to access it to make sure that the test ports is alive before you do more complicated testings. Right? Those are all the orange boxes that I represent in each of the chiplets. They could be JTAG and parallel test port for scan. The third thing, which is the black box, is a power, clock, and reset delivery. You need to make sure that every chiplet able to align, able to have a clock, functional clock, reset, and the power being delivered. Because the way you deliver the power will be different between chiplet and package, like what I mentioned, right? The interoperations, the right controls, things like that. Die-to-die interconnects, right? You need to check for open shots, crosstalks, and high margining, right? You need to be able to do that, able to have a way to distinguish this kind of 4 methods of failure. So these are the 4 things that you need to be able to segregate them in your test program, right? For assembly, test access, is it a clock issue, reset, PLL, initialization, power delivery, die-to-die interconnects. Once you have checked all of these properly, then only you should start doing your test. You can do your logic test, because once you reach here, which means your die is assembled perfectly, you can access your chip, you can initialize your chip, your die-to-die is good. Then you can start doing your coverage testing or performance testing. So the key thing is that all this is not free, right? You need to come with certain DFT hooks that not only for tests, but you need to have a way to provide the diagnosis feedback during the product debug, right? So I'm going to talk about zoom in a bit more of what are the DFT capability that support this debug and fault isolation. So I have 4 things to share with you all. The first thing is about bare minimum bring up of the chiplets, right? Because sometimes you want to be able to simplify your bring up when you go into the complicated chips. Simplification of bring up, which means it could be different from the actual platform because you need to be able to debug it quick. For example, power delivery. Sometimes you may have a voltage regulator that deliver the power from your active interposer to your chiplets. You want to be able to work by default. When you power up, your regulator can send the power to the chiplets without any change of the default states. And you need to have a way to simplify your clock and reset generations. For example, can I do certain operations without PLL? Just simple clock that drive from the package balls to the active interposer or through the active interposer to the chiplet without any PL dependency, because sometimes PL may be complicated, right, in debug. Test access mechanism is JTAG test port. You want to be able to have a way to check it. Typically, loop back test mode at test port speed is the most recommended. What I meant here is that, for example, you have a JTAG. Typically, you don't do a simple ID code. You just able to put the power, wiggle the TCK, TMS, TDI, get the ID code. If you're able to do a JTAG ID code in each of the chiplet, with the power, you're able to achieve the condition of checking the test access. For a scan test port like 1838 or any SSN or any simple test port, you need to be able to send the data and loop it back to make sure your connectivity is good. You must check the connectivity before you do more complicated, because sometimes you could have a failure due to the connectivity. You could have defects because of the interconnects, right? So the third thing is about die-to-die interconnects has sufficient diagnostics. Yesterday, my colleague Srijit, he did talk about die interconnects test. So this is more towards how do you debug a die-to-die interconnects, right? You need to have different data pattern types, which die-to-die signal is failing. You need to have a way to margin clock and data relationship. I'll have one foil to talk about later. The fourth one is a very, very, very important, which is interoperability. This is a very famous word that everybody uses when it comes to 3D IC, right? You need to have, how do you handle cross chiplets and active interposer? So there are 4 things. You need to have the direct JTAG overrides. Very important, you need to be able to isolate your active interposer from a chiplet. This is needed to achieve equivalence with the die level and the package level. Isolate means you do not want to have anything from the chip top die interfering with the active interposer when you're testing the active interposer. And you want to have disable all the handshake within a chiplet so that you can test each of the chiplets independently. And you need to be able to enable or disable each chiplet. Sometimes you want to say, hey, maybe there are certain, when you run all the chiplets, maybe, you see a failure. So you want to try, okay, can I disable one, to see whether does a failure goes away. It could be certain thermal related issues as well. So these are the 4 things that we need in order to handle interoperability. So these are the 4 major things: bare minimum bring up, test access mechanism, die-to-die diagnostics, and how you handle interops. All right. So this slide talk about how you debug die-to-die diagnostics, a kind of a case study, right? If you look at this, number 1, in the die-to-die, let's say you have a failure. You run through the die-to-die test. You see this is not a stuck at failure. It's very obvious, right? You see a red and green region. It's more towards like a frequency failure, which means that if I run at a lower frequency, I see a pass, which means at speed is failing. So when you see this failing, what are you going to do? Because typically in a die-to-die environment, die-to-die is unidirectional, right? So usually we test based on the mission mode. So it could mean that it is an interconnect failing, or it's a silicon, the die, there's the buffer that's failing, or there's certain margining capability. So you need to have a diagnostics mode, right? You need to enable various diagnostics pattern to pinpoint the failing node. If you look at number 2, right, we need to have a kind of a simple truth table. One thing is that both dies need to have the similar DFT, right? So that you can, for example, in this kind of die-to-die testing, you need to have a way to do a look back within the die so that you know, is it a die problem or interconnect problem? If you have a different DFT, like let's say in die A, you only can do look back, die B, you cannot do a look back, you only can do unidirectional, then you'll be stuck. You'll be wondering where's the failure, right? So if you have a similar capability, then you can, build a fault model that you can help to pinpoint. In this case, by exercising all these diagnostics pattern, right, we found out that the failing path in this example, it could be a B to A, and it's a timing path, right? So key message is that without sufficient DFT, right, you're going to have a very difficult time in order to root cause. Imagine if imagine on die B, you cannot do a loop back test. You're going to be stuck you only can do 3 things, and you'll be wondering what happened. All right. So this is an example of critical diagnostics. You can test, but you cannot diagnose if you don't have the similar DFT capability between the 2 die. All right. Now, the last one is about system. Just like I talk about diagnostics of the die-to-die. The third one is about more interesting. Let's say, you have a field failure. Typically, when you have a field failure, you need to reproduce the failure in-house in system level tests. Typically, you do it through JTAG. It's a very common way for you to debug through the system. And in a system, you need to know which block is failing, right? You need to, is it which chiplet is it failing? Is which block, and is it sensitive to temperature, right? And then in most cases, sometimes you may want to run your ATE test onto the SLT. For example, maybe I want to run MBIS test, logic BIS test. Maybe there's certain SLT environment in terms of power delivery, in terms of power droops that may cause a failure, right? So these are the 3 things that you want to reproduce. Once you're able to reproduce it, right, as you know which block, you are trying to find, because you want to, maybe this could be a defect that, we did not cover, right? So you want to able to see how do you bring it back to AT. This is a complicated one. How do you duplicate to AT and do an FA? When I say that, hey, if the failure is on an active interposer, you can't do an FA. What are we going to do about it? Well, the first thing is you need to be able to duplicate the failure. So I give an example. If you look at this example, this is a simple active interposer where CPU, GPU, and SRAM, and then you have an I/O IP. So let's say you have a failure in this interface. By going through this, system level debug, you pinpoint that, okay, my failure is on the active interposer. The failure happened in this I/O. Then when you go back to ATE, typically, if you have this, you're going to say that, oh, I cannot reproduce through my test program. All my scan tests all are passing. So which means that you need to be able to duplicate the kind of functional transactions onto the active interposer. So my kind of way to look at this is that any functional test that we need to perform on the active interposer, we want to be standalone. Very important, because so that you can bring it back to die level and you can do better debug, right? So in this example, you know that this failure on the I/O interface IP is coming from interaction with the CPU chiplets, GPU, or some SRAM. So you need to have a DFT mechanism to isolate, which I mentioned early on, and a block in the active interposer, which I call it functional DFT injection block, where this one you can inject downstream cycles that mimic a CPU cycles, a GPU cycles to the I/O interface IP. Then you can have a local SRAM that kind of do the function of the top chiplets. If you have this green box and you're able to do isolation, you should be able to bring the failure from system to ATE within the active interposer, which means that you can even bring it to the die level. Sometimes you want to screen the die level to improve the quality, right? So this is I call it shift left approach with the aid of the DFT, all right? Okay, so I've covered, what are the things, the best practice we need to do at die level, test program, the inline detection, 4 things about the design for debug. We talk about die-to-die diagnostics, and we talk about the shift left, from a system to the die level. So I want to talk about what are the things that industry should consider, from the debug point of view. Because in a multi-vendor chiplet product, right, debug and fault isolation must be added to the standards. Today, most of the standards only cover tests. And when you have multi-die from, people talk about now your chiplets coming from different company. If you have a multi-die from one company with a misprocess, we can control. But imagine you have coming from different die company, how you integrate different debug modes, right? You need to have a standards. And 1838 today, focus mostly on test, and we need to make sure that it include the debug and bring up, right? And there's this IEEE P2929, which is focused more on the debug, can extend to do chiplet debug requirement, at die level, package and system. And any die-to-die interconnect or DSA, a bunch of wires, need to come with ATE diagnostic best practice, right? And any analog IP suppliers should have die-level tuning ORS via JTAG and any die-level observability, right? And the last one, which JTAG is often used in a product bring-up, right? At any socket, die, tester, and system to debug and access and dump out internal registers. So it is very important, since you're going to have multi-vendor chiplet product, the industry will need to develop a format, of course, with certain security considerations, to exchange and access internal registers. This is something like style file, right? Style file is a universal stimulus for test. So now we can look into how do I have a universal format where you can draw the register informations from different chiplet, from different company, right? That you can use it to debug, and to root cause of failure, right? All these things means that the industry need to specify an interoperation standards that chiplet can work together, not only for tests to bring up sequence and debug for low yield, DPM, and RMA. So these are the call for actions that I have. All right. To wrap it up, debug and fault isolation is a key aspect when it comes to test. The test flow need to have inline fault detection and isolation. Shift left to die level test is key when it comes to test, repair, debug, and binning for 3D integration, right? And chiplet marketplace need to transfer all this information from die supply to package and system integrator, right? And existing IEEE standards for 3D test need to evolve to comprehend debug and fault isolations at die, package, and system. So a little bit of advertisement, working with Abraham and Zoe and company. Coming 2021, our Electronic Packaging Society Test Committee, we are publishing a one-stop shop for requirements on 3D IC test and debug. So the things that I mentioned, there'll be more details mentioned in the handbook. So check it out. With that, I concluded my presentations. Zoe, back to you.
Thank you, Terrence. That was very interesting. We have a couple of questions in the Q&A. The first one is from Jan Vardeman. How does this change? This question came in quite early in the presentation, so just to set the context a little bit. So I would say, how do things change if the chiplets are connected with direct hybrid bonding instead of microbumps? Okay, good. So the question, just to repeat, is about hybrid bonding, right? So let me just go back to, let me use, I think, this picture. Hybrid bonding and microbumps is more towards like how it's still a die-to-die interconnects, right? Just that I'm doing metal, right? Without bumps. In other words, the density of interconnect will increase, right? So which means that what you need to do is that you're going to see more failures, right? On the die. So your die-to-die interconnect test will need to be more, how to say, include mechanism to detect
like crosstalk kind of failures. I believe that was kind of covered in the yesterday's sessions, because when you have hybrid bonding, you're going to pack more. So your repair mechanism probably need to be smarter. You need to have a repair mechanism, right? It's more to overcome the yield. The way you access your chiplet is still going to same, because still die to die. But you need to have a way to screen the assembly and probably to recover yield through a more, I would say, more robust repair mechanism, and have a way to detect for things like crosstalks, are very important. This is how I see how it changed when you go from micro bumps to the hybrid bonding. That's number one. The second thing, at the die level, your probing solution will change completely when you go to hybrid bonding. The probing that you do for microbump will not apply to hybrid bonding. So I believe there are industries work happening as we speak to address this.
Okay, thank you. There was a second question came in from Syed Manzoor Kazim. When can we expect all of these features incorporated into the standard? And I'm assuming that's the P2929 that you talked about.
Yeah.
Maybe Terrence, could you give a little bit of context on that standard? What before? When did it start? What's the main subject in that?
Sure. Actually, P29 standard is quite new. Is where I got to know this recently. It's a standard where we focus on, we call it scan and array dump, right? It's not publicly known yet, but you can find out it's run by Dr. Sankran Menon of Intel, right? This 28 is more of a debug mechanism for scan dump. So I'm not sure when is it good, but I know there's discussion ongoing right now with a few committees. Definitely, right now I do not know when it's going to be, incorporated, but definitely, I have provided feedback to make sure that all these scan dump, need to incorporate chiplets.
Okay.
Yeah.
Thank you. You also mentioned, I think, in your summary that existing standards need to change. Can you elaborate on what changes should be recommended to those standards?
Yeah, I think if you look at the standards, it's more towards that how this interoperation works, right? So, for example, when you let's say today we have standards to access all these barrel test board, GTAC test board. So the standards need to specify how the interoperations need to be handled. For example, I mentioned, okay, how do I want to achieve isolations, right? What the standard is, okay, I want to achieve isolations, how do I do that? What is a mechanism to achieve isolation? What kind of gating? What's the mechanism to achieve isolation, right? Is it through certain gating, through certain active cell, right? Maybe all your boundary signals need to have some kind of overrides. So there are many ways of achieving, some kind of isolation schemes. That's what I mean by, standards.
Okay, yeah, I understand. Okay. I think we have about 1 minute left. If there's any quick question.
Maybe I add a bit of the standards, right? So yeah, the standard need to more of like provide some kind of debug hooks, especially on how you isolate the interposer. For example, if you talk about this, maybe you would say that we have like a common schemes of overriding a rule of saying that, okay, you need to have a safe state for all the signals coming from the top chiplet into the activator, some kind of rule, right? Maybe that you want to say that between the two chiplet, any handshake you want to disable, right? And maybe another thing is that, you want to have another way is that you need to have a way to disable the chiplet. It's something like kind of something like a debug kind of standards, right? In order for you to survive, to control and to observe in the debug. That's what I mean by standards, interoperations and so on.
I see. Very good. Thank you. Thank you, Terrence. That was a very interesting presentation. I think that was the end of the questions.
I'd like to thank all the presenters who presented today, and I also want to give an extra special thank you to all the sponsors who made this event possible. Our diamond sponsor is Amcor with differentiators in technology, quality, and service. Our Emerald sponsors are Advantest, rated #1 in the VLSI research for ATE survey. Synopsis from Silicon to Software. And our Ruby sponsor, Tech Search International. So I'd like to thank all of them once again for making this event possible. I'd like to thank all of you for attending and look forward to seeing everybody here back again tomorrow. So thank you and have a good rest of your day.